Welcome to this session on electrical circuits and devices. Today, we are diving into the fascinating world of digital numbering systems, the foundational language of all modern computing. To start, let's look at how digital systems operate. At their core, most digital systems rely on just two possible signals, 0 meaning off and 1 meaning on. We call this binary. While the real world is analog, the devices we use process information internally in the digital domain. A number base simply tells us how many unique symbols are used to represent a value. We are all very used to the decimal system, which uses 10 symbols. But in computing, we also rely heavily on binary, which is base 2, octal, which is base 8, and hexadecimal, which is base 16. Let's quickly remind ourselves how the decimal system works. Each position in a decimal number represents a power of 10. For the number 1,439, we have 1 in the thousands column, 4 in the hundreds, 3 in the tens, and 9 in the ones. We will apply this exact same positional logic to other number bases. Why do computers use binary? It comes down to hardware. Computer processors use microscopic transistors acting as switches. If the switch is open or in cutoff, it represents a 0. If it's closed or saturated, it represents a 1. By combining billions of these simple switches, we can build complex processors capable of incredible calculations. Any real number, text, or image can be represented as a binary string, often called a word. A single 0 or 1 is a bit. 4 bits make a nibble, and 8 bits make a byte. As we scale up, we use terms like kilobyte, megabyte, gigabyte, and terabyte, each representing progressively larger multiples of bytes. When reading a binary number like 0110, we read from right to left in terms of value. The bit on the far right is the least significant bit, or LSB, because it holds the lowest value. The bit on the far left is the most significant bit, or MSB. Each position represents 2 to the power of n-1, where n is the position number. Let's convert that binary number, 0110, into decimal. Starting from the right, the first position is 2 to the power of 0, which is 1. The next is 2 to the power of 1, which is 2. Then 2 squared, which is 4. We simply add the values where there is a 1 bit. 4 plus 2 equals 6. To go the other way, from decimal to binary, we use repeated division by 2. Let's convert 24. We divide by 2 and record the remainder. 24 divided by 2 is 12, remainder 0. We keep dividing the result by 2 until we reach 0. Reading the remainders from bottom to top gives us our binary number, 11000. Adding binary numbers follows simple rules. 0 plus 0 is 0, 1 plus 0 is 1. The only trick is 1 plus 1. In decimal, that's 2, but in binary, there is no 2 symbol. So 1 plus 1 is 0. Carry the 1 to the next column, just like you would carry a 10 in standard addition. Subtraction is similarly straightforward. 1 minus 0 is 1, and 1 minus 1 is 0. If you need to subtract 1 from 0, you must borrow from the next highest position, exactly as you do when subtracting a larger digit from a smaller one in decimal math. As binary numbers get larger, they become very hard for humans to read. To solve this, we use hexadecimal, a base 16 system. It uses the digits 0 through 9, and then the letters A through F to represent 10 through 15. The beauty of hex is that one single hex digit perfectly represents exactly 4 binary bits. Converting a long binary string to hex is easy. First, split the binary number into groups of 4 bits, starting from the right. Next, convert each 4-bit group into its decimal equivalent. Finally, swap any decimal number from 10 to 15 with its corresponding hex letter. Our long binary string simply becomes the hex word FADE. To convert a decimal number directly to hexadecimal, we use the same repeated division method we used for binary, but this time we divide by 16. For example, 350 divided by 16 gives 21 with a remainder of 14. 14 in hex is E. We continue dividing until we hit 0, giving us 15E. Another system used to compress binary is octal, which is base 8. It only uses the digits 0 through 7. Because 8 is 2 to the power of 3, every single octal digit perfectly represents a 3-bit binary sequence. Converting binary to octal is just like converting to hex, but instead of grouping by 4, we group the binary string into chunks of 3 bits, starting from the right. Then we simply convert each 3-bit chunk into its decimal equivalent, which gives us our final octal number. To convert an octal number back to decimal, we use positional weighting, just like we did with binary, but using powers of 8. We multiply each octal digit by its corresponding power of 8 and add them all together to get our base 10 decimal value. And for converting decimal to octal, we once again use repeated division, this time dividing by 8. We record the remainders at each step, and reading them from bottom to top gives us our octal number. It's a universal method that works for any number base. To wrap up, remember that while computers speak in binary, we use systems like hexadecimal and octal to make those long strings of zeros and ones manageable. For your independent study, I highly recommend researching ones complement and twos complement, which is how computers handle negative numbers in binary. Great work today.